Man, it's so hot in here. Maybe it's because I have the air conditioner turned off so it doesn't mess up my video. And it's Texas and it's the summer. But anyhow, it seems like it also means that we're ready to talk about temperature effects. And so I have my little example here with my beam, right? And so we want to talk about temperature effects. So what happens if I fix my beam and I were to light a little fire on it? Alright, I better not do that too long or else I'm really actually going to burn myself. What do you think is going to happen? Alright, well, I think we have some concept that when we heat things up, right, they typically expand. So, especially when we're talking about a homogeneous isotropic material like our metals, so like steel, aluminum, brass, these types of things, they typically will expand when we apply heat to them. All right, so how will it expand? All right, let's go ahead and sketch a picture. I want you to think about how that's going to expand. Let's draw a free body diagram for this beam that has a temperature effect applied. So what does the temperature effect look like, right? So I think it looks something like let's say a little fire here. So let's set our fire up here. And we're slowly going to heat this up, right? And I want to consider the case of uniform temperature expansion. So let's say it's expanding from all directions, right? This fire is around my member. We said that it's going to expand, and if it's all around, it should expand uniformly. What does that look like here? Well, since this is a fixed end, it's not going to change at this point, but at this side where we're free, it's going to expand outward. So we might expect a deflection, something like this. And we'll call this deflection delta temp. So this will be the deflection due to a temperature change. All right, we already stated that if a material is homogeneous and isotropic, like our metals or steel or aluminum, all these things that we typically use to fabricate things in engineering, that the deflection due to the temperature change is typically linear. And so we can say that delta temp equals, our formula is alpha L delta T. All right, what are these variables? Well, alpha, let me try to save this here. Alpha equals the coefficient of thermal expansion L is going to equal our initial length. So L is shown in our free body diagram up here. And delta T is going to be our temperature change. All right, just to make a note on some units here, alpha has weird units. The units on alpha are strain per degree Fahrenheit or strain per degree Celsius. And now remember, strain itself is unitless. So I like to think of it as it's strain per degree Fahrenheit, but a lot of times when we see this variable, it'll just be like some number with a little division sign, like per degree Fahrenheit or per degree Celsius, depending upon what unit system you're looking at. So I'll I'll jot in strain there. Length is just going to be in whatever unit system you're looking at, and temperature as well. For temperature change, we want to note that we will typically use positive for temperature increases, and negative for temperature decreases. And so we do that to correlate with our sign convention, right? We use positive because if the temperature is increasing, then the deflection is increasing, and a positive number would mean extension of our member. Whereas if it was getting colder, the member would be shrinking, and so then we would use a negative value, and then that would tell us negative. When we get our final deflection for delta temp, it would be a negative number, which implies contraction. And so this is kind of our sign convention. So this is our unit sign convention. The final thing I just want to point out is that this delta temp, right? Remember when we talked about loads, when we talked about the force, we said that we could come up with the deflection due to a force, and we said that that deflection was delta equals PL over EA. And so that was Hooke's law, and that was what we said was a material law for our particular engineering application. So whenever we deal with temperature effects, this will kind of be our new material law. So we're still going to go through equilibrium and kinematics, but then when we get to material law, when we deal with the temperature, we'll use this material law. When we deal with forces, we'll use Hooke's law. All right, so let's hop into an example, a real-world example of a bridge that's being heated up. Check it out. Imagine you're visiting St. Louis on a hot summer day. You see a beautiful steel arch. It thrills your soul. You look around at all the beautiful buildings, but it's getting warmer. It's so hot. You see the baseball stadium. It's too hot to go to a game today. You see beautiful bridges over the Mississippi River. And there, this bridge catches your eye. It's just a simple bridge. Could we model this bridge as being fixed on both ends? But if so, this heat, what is the heat doing to it? Would this beam expand, causing unwanted stresses due to this temperature? We must find out. Hopefully you agree with me that this is a very real problem, especially, I live in Texas where we have big temperature changes in a single day. So it's not unheard of for us to change 50 degrees Fahrenheit in one afternoon. And so what would that do to our beam if we started in a very cold state, and then as the sun came out and heated the bridge up, it increased in temperature by 50 degrees? I think you can imagine that the girder would expand, right? But if I have it fixed at both A and B, as the girder tries to expand, what will happen? Well, it's likely that the girder will develop compression in the beam, because as it tries to expand, because I have fixed or very rigid walls, it can't expand anywhere. It's not free to expand on either end. And so then we're going to develop a very large compression force in the member. And let's just see from the 50-degree temperature change how much compression we're likely to develop in this bridge girder. That's the setup for this example problem. So we have a steel bridge girder with a cross-sectional area of 25 inches squared that has a temperature increase of 50 degrees Fahrenheit. And the material properties are given as shown. We want to come up with the average normal stress in the beam. I think we can recognize that this is statically indeterminate, and so I want to take the opportunity to apply the force method again to solve the statically indeterminate structure. So again, in the force method, we take a complex problem and we break it down into smaller, simpler problems that we can solve so that the results add together to give us that complex scenario. So in our initial scenario, we have the bridge girder that is bound on both sides, and it's subject to a temperature change, an increase of temperature of 50 degrees Fahrenheit. This will cause the bridge girder to expand, but if we are to assume that there's a fixed rigid wall at points A and B, then the rigid wall will prevent the girder from expanding and therefore impart reactions AX and BX to the beam. All right, if I have two unknowns, but I would only have my one sum forces equation, that's what makes this statically indeterminate. So, like I did previously with the force method, I want to break this into two smaller problems. So first, I'm going to eliminate the wall at B. So what would happen if I was only connected at A and I applied the temperature increase? But that's not real. I really do have a reaction at B. So in my second free body diagram, I want to include the effect of just the reaction at B. So you see that my temperature effect is accounted for in my first free body diagram, and my reaction force is accounted for in the second free body diagram, and together those two cases will add back to my original case. In the case of a temperature increase where the bar is free to expand, we would expect the beam to get larger and expand to the right, a distance that we'll classify as delta temperature or delta temp. With regards to the reaction at B, I would expect the beam to compress when a reaction acting to the left at B pushes on the beam will compress. And together, those two deflections, delta temp plus delta Bx, have to equal my original deflection at B, delta B. And in this case, since there is no gap between point B and the wall, delta B will equal 0. So that gives rise to our compatibility equation. So we say that delta B is equal to delta temp plus delta Bx. So that's delta due to the force, Bx. So let's calculate delta temp. We're going to use our new material law that says delta temp equals alpha L delta T. So this equals alpha, which is our coefficient of thermal expansion. For steel, that is 6.60 times 10 to the minus 6 per degree Fahrenheit. Or remember, this is like strain. This is the amount of strain per degree Fahrenheit. We can then multiply that by the initial length of our bridge girder, which was 100 feet. And I would like to convert 100 feet into inches so that we have a displacement that makes a little bit more sense. It'll be in terms of inches instead of feet. And finally, I'll multiply by my change in temperature, and since I'm heating it up, I will use a positive 50 degrees Fahrenheit. The positive will indicate that delta temp is increasing. The deflection due to the temperature change is increasing because a positive temperature change will cause expansion in the member. If I take my numbers and I plug them into my calculator, I solve that delta temp is equal to 0.396 inches. So this 50 degree Fahrenheit temperature change causes the bridge girder to expand 0.396 inches outward. Now I need to calculate delta due to the force Bx. Now the force Bx causes compression along the entire length of the bridge. And when I look at the material law for forces, I know my material law is Hooke's law, PL over EA. So I plug in my axial force. The axial force in the member is equal to the reaction Bx, and it's going to be negative because it's in compression. For the length, I plug in 100 feet times 12 inches per foot. So again, converting my length to inches. My modulus of elasticity for steel is 29,000 KSI. And my area is 25 inches squared. And this is a very typical area for a bridge girder that would be 100 feet in length. Delta Bx is then equal to a negative 1.65517 times 10 to the negative 3 times Bx. Make sure you get that negative sign in there at the front. Again, negative sign because indicating compression, or that the force Bx is causing contraction in the beam. All right, with these results, we're ready to go back to our compatibility equation. Our compatibility equation says that delta B equals delta temp plus delta Bx. Delta B is 0 in this case because we have no gap between the beam and the wall at point B. So if we did have a gap, we could account for it here in terms of including a real number here for delta B. In this case, delta B has to be 0. And then we plug in delta temp, which is 0.396 inches, plus the negative 1.65517 times 10 to the negative 3 times Bx. Again, I encourage you to keep as many decimal places as you can to maintain accuracy in coming up with this force. The reaction Bx is going to be equal to 239.25 kips. To solve the reaction at A, let's draw a free body diagram of the original problem. So we have a bridge girder that is bound on two sides, and it will then have reactions due to the temperature as the girder expands. It'll have reactions AX and BX as shown. So using my sum forces in the x direction equation, I can say that AX minus BX has to equal 0. And therefore, AX will directly equal BX. So AX will be 239.25 kips acting to the right. Finally, we're interested in the stresses in the beam due to this temperature change. So stress, we remember, is the axial force divided by the area. So in this case, our axial force is compression, negative 239.25 kips, and the cross-sectional area is 25 inches squared. So doing the mathematics, we solved that the stress due to the temperature change was negative 9.57 KSI, or kips per square inch, of stress, and that is in compression. Wow, our calculations told us that we developed about 9.57 KSI of compression in the member. Now, if we remember our material properties for steel, that's like, most steel beams are probably like a yield stress of 50 KSI. So, 9.5 KSI, that's like, almost 20% of the capacity of this beam is being taken up by just the temperature change from the sun. Right? Crazy, right? Is this something we really need to worry about when we design bridges? Well, I can already see that you're thinking about this, and you're thinking like, I'm not really sure if this is something I have to worry about. And probably from your experience, you know that a lot of times when we did statics, right, we looked at simply supported beams. And so a lot of times in bridges, we don't have this fixed condition that we proposed in the example problem. We really use a pin and a roller, right? And what does the roller allow us to do? Well, as we heat the member up, right, the roller allows the beam to expand in the x direction. And so we don't develop those compression forces because it can actually expand. And if you've gone over a bridge or two in your life, you probably have noticed that a lot of times when you approach the bridge span, there are expansion joints. So because the beam can move back and forth across these rollers, we have to accommodate that in the deck. And so we have these expansion joints to allow the bridge to separate and to come back together so that we don't have to worry about these large stresses due to temperature changes, and then our beams can just be focused on holding up the load that they're designed to support.